And here we are. This is section 4.1. This is where we've spent most of our time finding derivatives. Now we're going to start applying what we can learn from functions in the world around us using derivatives. Okay, so we're going to start off with a quick review. Back in pre-calculus, you guys were told about absolute maximums, absolute minimums of functions, as well as what made a local minimum and a local maximum. Okay, so when I'm looking at this function down here, I take a look. I want to try and find where is the absolute maximum located. And what I'm noticing is absolute maximum of a function is where it reaches the highest point, okay, in my domain. Here's my domain. It only goes from A to B. Here's my highest point of my function. So this right here is an absolute maximum. Okay. And with an absolute maximum comes an absolute minimum, the lowest or smallest point, okay, in my domain of my function. Okay, and I start looking at the lowest point, and it's over here, and this becomes my absolute minimum. Okay. But then we have these other ones where we call what are called local. Okay, local maximums and local minimums. Those are places in the graph where I reach a peak or I reach a valley, and I have to start thinking about, okay, is it as high or is it low? Okay, so when I take a look here, what I do is I take a look at the neighborhood. So I kind of cordon this off. I say, hey, at this point right here, is it a high point or a low point? And it's a high point. So that is a local maximum. It means the places around it is as high as it gets. Okay. Likewise, if I look here at this point right here and I look in the neighborhood around it, it is a low point or a local minimum. Okay. But what about this endpoint over here? This part right here. I take a look at its neighborhood around here. Notice I don't have anything off to the right. So I have to take a look at, well, what about just the neighborhood over here? Everything above me is higher than this, so because of that, it is a local minimum. Okay? And all the words up here are just the fancy math words for it. Okay, where an absolute maximum is saying it's on the domain if and only if that particular f of c is greater than all the other function values, which is true with this one. There's no other function values greater than it. Okay? So here we go. I'm going to move on. So what takes apart about this is where can I find absolute maximums and absolute minimums? It all depends on what my domain is. Okay? So when I take a look at the domain, all these functions are x squared, but my domain changes for each of them. So on this one here, you might want to label these to correspond with there's A, that's B, this is C, and this is D. And what I'm going to be looking at is I'm going to say, okay, so for my domain that's going from negative infinity to positive infinity, do I have an absolute maximum? Yes or no? Okay. In this particular case, there is no maximum, right? Because every time I keep going higher, keep going to the right, I can keep getting to a higher value. So there's nothing out there that is the highest of them all. So there is no absolute max. But there is an absolute minimum. My absolute minimum occurs down here. Okay? And so what I want to do is I want to get you guys trained in the fact of how to phrase this. So there is an absolute minimum of 0 at x equals 0. When I'm talking about absolute minimum and absolute maximum, I'm talking about the function value. When I want to know where they're located at, that's the x value. So again, the questions may be, where is f of x? Where is an absolute maximum? And that would be asking, where is, that's the x value. When it's asking, what is the absolute maximum value of a function? That is the y value. Okay? So then when I go ahead and I'm looking here, now I look at B. Now what B did is they restricted my domain. And if you're having trouble seeing this, these are brackets around here, which means that they're included. So I'm including 0, including 2, and everything in between, the rest of the graph I don't care about. So in this particular case, I do have a maximum because my domain is only up to here. So in this one, I do have an absolute max of 4 at x equals 2 and an absolute minimum of 0 at x equals 0. But then what happens over here at C? Over here at C, it's kind of a open and then closed. So again, open and then closed. Okay, well, I still have my absolute max. That's easy enough for me to see. That hasn't changed. So I still have an absolute max of 4 at x equals 2. But what about my absolute minimum? So I'm getting really, really close here. Here I am, I'm getting close, getting close, getting close, getting close. Will I ever get to that point? No. Okay, I'm never going to get to that minimum value. If I'm stuck there at 0.0001, I can always get a little bit lower. So there's no absolute minimum. Okay? No absolute minimum. And then, so what happens at D? Well, at D, they're both being open. So they're both open. And so at this time, you should be able to get it from now, or get it now. There is no absolute max or min. Okay, so let's take a look at some theorems that we're going to be using here. Okay. So some theorems, okay. First one is going to be the extreme value theorem. This is a very important theorem. We're going to start using theorems. You need to be able to use this theorem. What I mean by use this theorem is in calculus we need to justify things or prove things. To prove things, you need to use theorems. So if I want to prove something, what I need to do or prove this, stuff about the extreme value theorem, first I need to show some stuff. I first need to show that my function is continuous. And then I need to show that there is only a closed interval. And if I show those two things, guess what? I get to say that there's both a maximum and a minimum value on the interval. Now that's pretty powerful. If I'm able to show the function is continuous and I'm able to show that it's on a closed interval, then I know for a fact that there's an absolute max and an absolute minimum. And that's amazing to just say, okay? So when I go over here and I look at this and I say, well, what does something like that look like? Well, here I am on a closed interval from A to B. I could have my maximum here or minimum here. Or again, if I'm on my closed interval from here, my absolute max is here, my absolute minimum is here. Okay? Again, closed interval. Okay? Closed interval. You can kind of see the idea. Okay? So these are just pictures to show us what this could look like. Some other things to think about. Okay. The other one is, okay, so what about local maximums and local minimums? Okay. Well, I can say if a function has a local maximum, okay, or a local minimum, and that local max or local min is an interior point, so let's take a look at that. Whenever I was in an interior point, don't ignore the endpoints here, okay? But look at just the interior points. When I'm at my interior points, look at my slope. My slope for every single one of these is 0. So what's going to happen over here, the interior local extreme value says that if I could have a local maximum or local minimum value at any interior point of its domain, which is very key, and if f prime exists, then f prime will equal 0. I can use can change it around. I can say that if f prime of c equals 0, okay, then I know I'm going to have some type of local maximum or local minimum there, and it may be absolute minimum or absolute maximum. Okay, so which gets us to the critical point, which again is another favorite. We're going to have to know this. I will be saying critical point many times. So when we're trying to find where else, okay, I was having these absolute maximums or these local maximums, local minimums. If I go back to my first slide here, I'll see that I had my absolute max, which also is a local max or anything of the sort, here. Well, here my slope is not 0. In fact, my slope comes to a point. And when we have to remember, what does it mean when a slope comes to a point? Does my slope exist? No. Okay? So my slope does not exist. And so that's a part of my critical point. And my critical point is a point on the interior of the domain in which f prime is equal to 0 or f prime does not exist. These are very critical things to be thinking about. Okay? Critical points, critical things. Little joke. Okay? We need to know this. You need to put hearts. Okay? This is important to know. All right? This is another important thing to know. It's kind of snuck in there. Okay? In summary, extreme values. Now, extreme values, what I mean by extreme values, okay, those are the absolute min slash max or the local min slash max. Can only occur at critical points and at endpoints. Very important. Okay? The last thing I want to say here real quick before I get into some examples is that there are some different words that I can describe absolutes and locals. Absolute, okay, can also be called global, and local can be called relative. Okay, so let's go ahead and take a look at some examples. So this first one is finding absolute extrema. So we're going to be using the extreme value theorem in this one. It says find the absolute maximum minimum values of this on the interval -2 to 3. So real quick, what I'm able to do is I'm going to do 3 easy steps. Okay, if I want to find my absolute minimums, first thing I need to do is I have to say, is this function continuous? Yes. That function is continuous, okay, on a domain, actually on all reals. Okay, so I would say f of x is continuous. Continuous, and is on a closed interval. Okay, so if it's on if my function's on a closed interval, therefore EVT applies. Again, as a refresher, EVT, my extreme value theorem, means, well, since I said it was continuous and on a closed interval, now I know that I'm going to have a minimum, I'm going to have a maximum. And guess where I can find those? I can find those at endpoints. So where are my endpoints? My endpoints are where it tells me they are with my interval. My interval, so that means that I want to check out where is the value of f of -2. What is the value of f of 3? And I go ahead and I plug those in. And when I do, I get this being the cube root of 4. And this is the cube root of 9. Okay, I'm going to save this for later. What I need to do now is I need to go ahead and find out, step 2, is to find my f prime of x. This is fairly straightforward. I find f prime of x is equal to 2/3 x to the -1/3. And for these problems, what I want to do is I want to rearrange my function or my derivative into a fraction, x to the +1/3. Because I want to do this analysis on it, I need to go and find my critical points. And again, as a refresher, my critical points are where f prime of x is equal to 0 and where f prime of x does not exist. Well, where does that happen? All right, so I think about where does that happen for my numerator. My numerator is at 2 equals 0. So if my numerator is 0, can my numerator ever equal 0? Can 2 ever equal 0? No, that cannot happen. So I don't have any critical points there. So again, f prime of x does not exist. Where does that happen? Well, that's going to happen when 3x to the 1/3 equals 0. All right, and that's going to happen when x is equal to 0. And again, I got to check, is that within my domain? In my domain here is -2, 3. Yep, that's within my domain. Okay, so then I've checked my critical points, and here's I've checked my endpoints. So my critical point, now I put that in my list of things to check. F of 0 is equal to, now notice I chose f of 0, not f prime of 0. I plug that in, and I get 0. And remember, that line that we just did on the last slide said the only place for extreme values are going to be at endpoints and at critical points. All right, so I've done that, endpoints and critical points. And then I know that since it's a continuous function on a closed interval, I'm going to have one of each, one of a maximum and one of a minimum. Okay, and so what I'm able to find out, okay, is that f of 3, let's see here, f of 3 is an absolute max, so I'm able to say is my function f of x has a absolute max of cube root of 9 at x equals 3, and my function f of x has an absolute minimum of 0 at x equals 0. Okay. All right. Next. I mean, we have to phrase them that way, just so you know. So we got that all taken care of. Now, as far as the other endpoint, it is going to be a local max or a local min. I don't know which. We don't have the tools to tell me that yet without having to take a look at the function. All right. So I'm just going to let you hang on that one. Besides, the question was asking me about absolute maxes and mins. Okay. Let's go to the next. Okay, this one here says find the extreme values. Again, extreme values means I need to find, okay, local and absolute if they exist. I need to find both. Okay, so in helping myself out here, I got to be able to find my endpoint slash domain. And my endpoints, they tell me nothing. Okay, but what I have to do is I have to think about my function here a little bit. Okay, my function, if it has problems, if all of a sudden x becomes greater than 2. If x becomes greater than 2, then I'm dealing with the square root of negative numbers. Same thing if x becomes less than -2. I have square roots of negative numbers. But what about, okay, what about 2 itself? If I put 2 in there, I get the square root of 0, which is fine for the square root part, but it makes my function 1 over 0, which is bad. So my endpoints, okay, can only be from -2 to 2. That's my domain. Okay, my domain. Is it closed? No. So the extreme value theorem does not apply. Okay, so because the extreme value is going to apply, I will not have both a min or a max. I'm not guaranteed that. I have to find that out. But I still continue with my point. Next one, step 2. Okay, which is finding f prime of x. Well, to make that a little bit easier, I want to rewrite f of x as 4 minus x squared to the -1/2. And I find f prime using my chain rule. It's a -1/2, 4, keep the inside the same, x squared, x squared to the -3/2 times the derivative of my inside. Derivative of my inside is a -2 x. Okay. What I'm going to find out here is that the -2 and the -1/2 are going to end up canceling themselves out to be +1. And what I have left over when I rewrite this is x over 4 minus x squared to the 3/2. Okay, great. So I go to step 3, find my critical points. My critical points again is when f prime of x is going to be equal to 0. And where does f prime of x does not exist? So where does f prime of x equal 0? Well, that's when the numerator equals 0, and that's when x is equal to 0. I checked, does x equal 0 inside my domain? Yes, it is. So those are good points. I like that. And then I have to say, well, when is that not? When does f prime of x does not exist? That's going to happen when f to the negative, f minus x squared to the 3/2 equals 0. Which when I solve is x is equal to plus or minus 2. And I have to ask myself, is plus or minus 2 in my domain? No, it's not. So I'm not going to count those as critical points. They are not critical points because they're not part of my domain. So the only one all I'm going to do is then take my one critical point, plug that in there. It'll be f of 0 is equal to 1/2. Okay. And now I need to figure out, is that a local min, a local max, an absolute min, an absolute max? What is it? And without having some other tools with us, we have to graph it. So over here, I'm going to go ahead and make a little sketch of the graph. And what I'm going to see here is that this is what the sketch of the graph looks like. And so right here, there's my 0, 1/2. And so that becomes saying that my function, okay, f of x, has an absolute min of 1/2 at x equals 0. Okay. When you sketch it or you find it, you're going to use your calculator to figure that out. Okay. Later on, when we find more tools, you won't be able to use your calculator. All right. Next. All right. Piecewise function. In a piecewise function, what you guys are going to have to do is separate these things. So again, I got to figure this out. First is, do I have any endpoints? Okay. And what is my domain? So endpoint slash domain. So when I'm thinking about endpoints, well, they don't give me any. And look, it goes, this is minus 2x squared. This is just a parabola. It's good anywhere. So I'm good with that. X plus 2 is just a line. It's good anywhere. I'm good with that. The one thing I do have to check is what's happening on either side there. I have to check what's the limit as x approaches 1 from the left, and what's the limit as x approaches 1 from the right of my function. Okay, I need to check that out for my domain purposes. Well, when I plug in 1 over here, I get 3. When I plug 1 over there, I get 3. So that means the limit from both sides is 3. It exists, so it's continuous. Okay, good. So what does that mean for my domain? That means my domain is good from beginning to end, positive and negative infinity. So step 2. Okay, find f prime. To find f prime of a derivative of a piecewise function, you take the derivative of each piece. Okay, and take the derivative of this, negative 4x. For x less than 1, yes, I only made that less than 1. Okay, as a reminder, we don't put equals to in the derivative. And then and for this one, this is 1. Okay, for x being greater than 1. So 3. Okay, we got to find the critical points. Again, for f prime of x equals 0, and for f double prime, prime of x, does not exist. So again, where does f prime of x equal 0? So I got to check both pieces to find out where it's 0. So I set both pieces equal to 0. I find out that's when x equals 0, and I have to ask myself, is that in my domain? Yes. Is that in the domain for that piece of my derivative? Yes. So that is a critical point. Next one I check, can 1 ever equal 0? No, that's never going to happen, so I don't have one. So then the next one then becomes, where does it not exist? So again, I look at here, well, this part, there's nothing that'll make the world blow up on this one, no matter what I plug in. Same thing for the 1. No matter what I plug in, it will always be 1. So there's no issues there. The only issue then becomes what's happening at 1. So that means, again, checking the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right of f prime of x this time. So I can see if my derivatives meet, my slopes meet. Okay, so this one here, I plug that in, that's -4, and this one is 1, which means I have a jump discontinuity in my derivative, which means my derivative does not exist there, which means that the point of 1, x equals 1, is a critical point. Okay, so then my two critical points that I have are 0 and 1. So again, I need to test those points. So f of 0 is equal to, plug that in, is 5. And f of 1, when I plug that in, is 3. But again, without knowing, doing some analysis that we don't have, okay, I'm not sure which is which. Now you can think about it a little bit, maybe play with it in your head and say, well, I can kind of figure it out. But you can always graph it, okay? So you graph this. This is, again, from -infinity to 1. It's an upside down parabola where it crosses at the 5. And there's my 3. And it exchanges here at the 1 and does something like that. So what you're able to say is up here, it looks like it's a local maximum. And here it's a local minimum because, look, it goes on forever this way, it goes up forever for that way. Right? And that's what we're going to do. We're going to say f of x has a local max of 5 at x equals 0, and f of x has a local min of 3 at x equals 1. All right, we're almost there. One last example and we're done. Okay. Extreme values for this function. All right. So again, I got to do step 1. Okay, endpoints / domain. So my endpoints, again, I don't really have any. So now I have to think about what's going to make this function explode. First one is, can the denominator make this explode by being set equal to 0? No, nothing will make that 0. Okay, then I have to think about what will make the natural log explode. Well, natural log explodes with any value less than 0. Okay, natural log's original domain, okay, x has to be bigger than 0. Well, that's great. Nothing will happen because the absolute values, that's fine. But what does happen is x equals 0. If x equals 0, all of a sudden this function equals 0, and the natural log is 0, world blows up. Can't have it. So my domain is x just cannot equal 0. Okay, so that's step 1. Step 2, I need to go find f prime. F prime of x on this one, okay, natural log, the derivative of natural log, is 1 over the inside, but that means flip this over x times the derivative of the inside, so that's a quotient rule, low d high, so 1 plus x squared times 1 minus high d low, x times 2x all over low squared 1 plus x squared. I do some algebra. The 1 plus x squared here cancels out that there. And then what I have up here, x times 2x is 2x squared. So I got 1 plus x squared minus 2x squared. So my top becomes 1 minus an x squared. My bottom becomes x times 1 plus x. I left it like that because I knew what was coming next for my derivative, or next comes up next to my next step, which is critical points. And for my critical points, again, I'm checking for f prime of x is equal to 0, and for when f prime of x does not exist. Well, when does that happen? Well, f prime of x is equal to 0 when the numerator is equal to 0. So when 1 minus x squared is equal to 0. And then I go ahead and I solve for that. I find out that x is equal to a plus or minus 1. And then I check, is that in my domain? Yes, yes it is. So both of these are critical points. Next I check for does not exist. Well, when does that happen? That happens when my denominator is 0. Or in other words, when x equals 0. And again, I ask, can that happen? Is that my domain? No, that is not in my domain, so it is not a critical point. However, I do have 1 plus x, squared. That's supposed to be squared. Okay. Does that ever equal 0? No, that won't ever equal 0. So, why won't that ever equal 0? Okay, so that will never equal 0, or excuse me, equal 0. That will never equal 0, so there's no critical points from there. So my only critical points now are f of 1 and f of negative 1. When I plug that in, I find that's the natural log of 1/2 for both of them. And again, without having other tools to be able to help myself out here at my disposal, I do need to graph this. So in graphing this, I graph it. And what I find out is my graph looks a little something like this. Alright, when it looks like this, here I am at negative 1. Here I am at 1. Okay. And what is that going to equal? What does that mean? That means that I have local maximums, or actually absolute maximums, at those two places. So, again, I write this out. F of x has an absolute max, okay, of 1/2 at x equals both spots, plus and minus 1. Whew, that was a lot. So that's it. I go over here. There's your homework. Go ahead and take care of it. We'll see you guys in a couple of days. Good luck. God bless.